Hi, in the past few modules we've been talking about the general linear model, and we've been talking about how we can model the design matrix and the variance-covariance matrix in order to get the best results using the GLM. In this particular module we're going to be talking about performing inference with the GLM. So just to summarize what we have a model, y is equal to x beta plus epsilon. We have a way of estimating beta hat, and the best linear unbiased estimator is given by the following. And we also talked about how we can estimate v and beta in an iterative fashion if we don't know v a priori. Now, once we have beta hat, we can get the fitted values. Y hat is equal to x beta hat, and we can use this to compute the residuals. So that's the data minus the fitted values. And so we write the residuals as little r is equal to y minus y hat, and we can re-express it in terms of x and beta hat in the following way. And finally we can write this as capital R times y. Now capital R is the residual inducing matrix, and lowercase r are the residuals. We're going to need this in the module today, so I'm going over this again for that purpose. So after fitting a GLM, we want to use the estimated parameters to determine whether there's significant activation present in that particular voxel. Inference in the GLM is based on the fact that beta hat is normally distributed with a mean beta and a variance-covariance matrix which is x transpose v inverse x, the inverse of that. So it depends both on v and on the design matrix. So using this result we can perform T procedures and F procedures to perform tests on different effects of interests. So we're often interested to see whether some linear combination of the parameter estimates beta are significant. And so usually we write the term C transpose beta to specify a linear combination of the estimated parameters. So C transpose beta is C1 times beta 1 plus C2 times beta 2 all the way up to Cn times beta n. So we choose C in such a manner to highlight certain linear combinations of the beta. Now C is called a contrast vector in this, and so here we're talking about looking at different contrasts of the parameters. So here's an example. Here's an event-related stimuli with two different types of stimuli. Say that there's stimuli A and a stimuli B, and we want to look at the difference between A and B. So the way we would fit a GLM model here is we would have one component corresponding to the baseline, so that's beta 1 is the parameter associated with the baseline. We would have beta 2 corresponding to the first stimuli type, and beta 3 corresponding to the second stimuli type. Now if we wanted to study the difference between the two, we would, for example, test the null hypothesis that beta 2 is equal to beta 3. There's no difference in the activation between stimuli 1 and stimuli 2. And if we reject this, then there is indeed a difference between the two stimuli. Another way of writing this in the terms of contrast, we can write this in the C transpose beta equal to 0, where C transpose is 0, 1, and minus 1. It's that vector. So if we do that, we get beta 2 minus beta 3 is equal to 0, which is equivalent to beta 2 is equal to beta 3. So that's a way of expressing this particular hypothesis in terms of contrasts. So how do we test this? Well, the typical way of testing this would be using a t-test. So to test the null hypothesis that C transpose beta is equal to 0 against an alternative that is not equal to 0, we would use the t-statistic. And so the t-statistic is simply the contrast of the estimated beta values divided by the standard error. So under the null hypothesis, this statistic has an approximate t-distribution where the degrees of freedom depends on the residual inducing matrix R and the variance-covariance matrix V. Using this result, we can compute p-values and threshold this particular t-statistic. Now we often want to make simultaneous tests of several contrasts at once, and now we can express C as a contrast matrix instead of a contrast vector. So for example, suppose we have 5 parameters in our model, so beta 1 up to beta 5. Now the following contrast matrix, C, which is equal to 0 everywhere except the 1 in the first row, first column, and in the second row, second column, would be equivalent, C transpose beta would be equivalent to beta 1, beta 2. So testing whether C transpose beta was equal to 0 would be testing beta 1 equal to 0 and beta 2 equal to 0 simultaneously. And that sometimes we want to do things like that in fMRI. So as an example, let's consider a model with a boxcar-shaped activation and drift model using a discrete cosine basis. So here the design matrix has 9 columns. The first column corresponds to the boxcar, the second column corresponds to a baseline, and columns 3 through 9 correspond to the discrete cosine basis set. Now suppose we want to ask the following question: do the drift components add anything to the model? Because if we have our druthers, we just use 7 parameters to estimate the drift. If there is no drift, we would rather not use up those degrees of freedom. So it might be natural to test whether or not the drift components add anything significant to the model. So in this example, we want to test C transpose beta equal to 0, where C transpose has the following shape. Now, this is equivalent to testing whether or not beta 3 up to beta 9 are simultaneously equal to 0. If this is indeed true, then we could remove these 7 columns from the design matrix, so they're not adding anything significant information to our model. So to understand what this implies, we typically split the design matrix into 2 parts. So we have X is split into X0 and X1. X0 consists of the first 2 columns, which is the baseline and the boxcar, and X1 consists of the discrete cosine basis sets. So according to the null hypothesis, the information contained in X1 isn't important. So according to the null hypothesis, we could just as well fit a model X0. So this is what we really do in hypothesis testing here. We compare a reduced model, which corresponds to using X0, versus a full model, which uses X0 and X1, which is what we called X before. So do the drift components add anything to the model? Well, since X1 matrix explains the drift, we want to ask whether or not it contributes in a significant way to the model. So we compare the results using the full model with design matrix X with those obtained using the reduced model with design matrix X0. This gives us the ability to test the hypothesis using an F statistic. Now the F statistic takes the following format, and as you'll see, it depends on the residuals R not from the reduced model, the residuals R from the full model, the residual inducing matrix capital R from the full model, and the residual inducing matrix from the reduced model R naught. And assuming that the errors are normally distributed, F has an approximate F distribution with the degrees of freedom given by the following formulas. So we can use this information to, again, threshold the images and calculate p-values. We do this hypothesis testing at every voxel of the brain, and so for each voxel a hypothesis test is performed, and the statistics corresponding to that test is used to create what's called a statistical image over all voxels. So in this example, I've performed a t-test at every voxel in this slice of the brain, and I've replaced the voxel value by the t-statistic value. So I have a t-map in this case, and you'll see that the yellow areas are areas with high t-statistics, and the red areas are ones with lower t-statistics. Now we can summarize our procedure for localizing activation. We start out by constructing a model for each voxel of the brain. This is the so-called massive univariate approach. And so regression models such as the GLM are commonly used. And so we set up a GLM model and get an appropriate design matrix as described in this cartoon. In the second step, we perform a statistical test to determine whether there's task-related activation present in the voxel. And so these statistical tests take some format as C transpose beta equal to 0. The result of this is a test statistic at each voxel of the brain. So at each voxel we fit a GLM model, perform a statistical test, and get a test statistic. The map of these are our statistical image. So this is a map of, say, t-tests across all voxels. And this is something that's called a t-map. This is a nice result here, but what we really want to do is we want to choose an appropriate threshold for determining statistical significance. So we want what's called a statistical parametric map. So we want to threshold this image in order to find which voxels are truly active. Well, those are going to be the voxels that, say, have a high t-statistic in this, if we're doing a one-sided test. And then we're going to color code each significant voxel in a manner corresponding to the size of its p-value. So this is going to tell you the strength of activation in each voxel. Now, looking at these statistical parametric maps are much easier to interpret than looking at the T-maps because we've gotten rid of all the non-significant voxels here. However, what we've done is we've had to choose a threshold, and choosing this threshold is a very difficult problem, as we'll see. So how do we determine which voxels are actually active? Well, there's a lot of problems associated with that. The statistics are obtained by performing a large number of hypothesis tests. And because of that, we have a multiple testing problem. So many of the test statistics will be artificially inflated due to the noise. And this will lead to many, many false positives. So this slide illustrates some of the problems that are going on here. Suppose we have 100,000 voxels, and we perform 100,000 hypothesis tests, and we threshold them at alpha equal to 0.05. Well, when we do this, we're saying that we're going to have a false positive 5% of the time. Well, 5% of the time in 100,000 voxels is 5,000 false positive voxels. And so we're going to have a lot of false positives, and we're going to have entire brain regions that are false positives. So what we really want to be able to do is we want to choose a threshold, maybe not at alpha equal to 0.05, but we want to choose a threshold that's a balance between sensitivity, i.e. being able to find the true positive rate, and specificity, i.e. finding the true negative rate. And so here we kind of illustrate this on our statistical map here. If we choose a variety of different thresholds, in the first threshold we're very lenient, and in this case we're pretty certain that we've found all the significant voxels, but we're also pretty sure that we found a lot of false positives here. You see that there's activations spread all over the brain. Now if we move to the right hand side, we have a more stringent threshold. In this case, we're pretty sure that this area here that's active is truly active, but we can't shake the feeling that we've also thrown out some other true activations because we've used such a strict threshold. So what we want to do is we want to find a threshold that finds a sweet spot between sensitivity and specificity. And this is a huge topic in fMRI data analysis, and we're going to be talking about this in the coming modules. Okay, so that's the end of this module. We talked about inference in the GLM setting. In the coming modules, we'll talk about multi-subject analysis and also multiple comparisons. Okay, I'll see you then. Bye.